Hello everyone, welcome back to a new video. Today we're going to be looking at the derivation of the Taylor series expansion of ln of 1 plus x. Now there are a few ways to derive this result. The first sort of main way, I guess, would be to sort of take an infinite amount of derivatives, do it that way. There is sort of a nice formula you can use. However, in my opinion, I'm going to show you a slightly cooler way. It's a slightly cooler way, in my opinion, which leads to the same result. So let's get into it. So first of all, we are going to start with the function, if I change colour here, 1 over 1 plus x. So we're going to start with 1 over 1 plus x. Now, how can we rewrite 1 over 1 plus x? Well, we can rewrite this as 1 plus x to the power of negative 1. Now we're going to expand this this function here binomially, because we have got a function to the power of a negative power. We can expand this. We know how to expand this using the binomial theorem. Now, the form that we're going to be using is the form, if we have 1 plus x to the power of n, then this expanded is 1 plus nx plus n times n minus 1 over 2 factorial x squared plus n minus 1, n minus 2 over 3 factorial x cubed, and so on all the way off into infinity. Now we only use this form if this value of n here is either a fraction or it's a negative power. So if it's just a regular sort of whole positive integer, then you would use the other binomial theorem, the simpler one. However, we're going to be using this one because we've got a power of negative 1, so we're going to be using the binomial expansion of this form. So let's go ahead and expand this term by term. So 1 plus x to the power of negative 1 is going to equal 1 plus, now n of course is our negative 1, so we're going to have 1 plus negative 1 times x plus negative 1, now n minus 1 is going to be negative 2 over 2 factorial x squared plus negative 1, negative 2, negative 3 over 3 factorial x cubed, and so on. I'm not going to do the infinitely many terms, that would be ridiculous. So simplifying this then, we get 1 minus x. Now this negative 1 times negative 2, that gives us positive 2, and we're dividing by 2 factorial. So 2 factorial is of course just 2 times 1, which is also 2. So the coefficient of the x squared is just going to be 1. So we're going to have plus x squared. Next, we are moving on to the x cubed term. So we've got negative 1 times negative 2 times negative 3. Well, that's going to be negative 1 times negative 2 is positive 2, times negative 3 gives us negative 6. So at the very top, we've got negative 6, and on the bottom, we've got 3 factorial, which is 3 times 2 times 1, which is positive 6. So we've got negative 6 over positive 6, which is, of course, negative 1. So we've got a negative x cubed. And I don't know if you can see, but this pattern of alternating positive and negative, it's going to continue forever, basically. So we're going to have plus x to the 4 minus x to the 5th plus x to the 6th all the way forever, all the way off into infinity. Right. Okay. So let's write down what we've got. So we've just expanded 1 over 1 plus x, and we got 1 minus x plus x squared minus x cubed, and that just continues off forever to infinity. So what we are going to do now is we're going to look at how 1 over 1 plus x is actually linked to ln of 1 plus x, because don't forget, we're not bothered about 1 over 1 plus x. We want ln of 1 plus x, don't we? That's what we want as our end goal. So we're going to look at the link then between 1 over 1 plus x and ln of 1 plus x. Now, I'm sure some of you can already see it, but it's the fact that if you were to differentiate with respect to x, ln of 1 plus x, you would get 1 over 1 plus x, like this, because the derivative with respect to x of ln of some function of x is equal to the derivative of that function divided by the original function. The derivative of 1 plus x is of course just 1, so we've got 1 at the top of the fraction here, and then f of x, so the thing inside of the ln, just goes down to the bottom. So if you differentiate ln of 1 plus x, you get 1 over 1 plus x. So this is good, because if we're starting with 1 over 1 plus x, we need to work backwards to get to that ln of 1 plus x. And the way, of course, we work backwards, basically doing the opposite of derivatives, is of course integrating. So we know that integrating 1 over 1 plus x with respect to x is going to give us ln of 1 plus x. We know that to be true. Plus c, but we're not going to be dealing with the constant just now. So let's go ahead and integrate, because we know if we integrate 1 over 1 plus x, we get ln of 1 plus x. So let's integrate both sides of this expression up here. So we're going to take the integral here and the integral right there. So taking the, I'll zoom out a bit so that we can still see the original function at the top. So taking the integral of 1 over 1 plus x with respect to x, we are going to get the integral of 1 minus x plus x squared minus x cubed plus x to the 4 all the way forever. And of course, we're going to do that with respect to x. Okay. So the integral, so looking at the left-hand side now, the integral of 1 over 1 plus x, we said, was ln of 1 plus x. ln of 1 plus x. And that's going to be equal to, okay, so now we need to integrate this infinitely long string of x's, basically. So the integral of 1 is, of course, just x. The integral of negative x is negative x squared over 2. The integral of positive x squared gives us negative, no, it doesn't, it gives us positive x cubed over 3. The integral of negative x cubed gives us negative x to the 4 over 4 plus x to the 5th over 5, and so on, negative x to the 6 over 6, all the way off forever. So now we've ended up with just another infinitely long polynomial. But the polynomial that we've got is better, because it's equal to ln of 1 plus x. So if we can condense this infinitely long polynomial into an infinite sum, then we're done. We are essentially done. So the left-hand side is, of course, just ln of 1 plus x. Now let's have a look at the right-hand side and see how we can turn that into an infinite sum. So we're going to have the sum. So this is the first position is when n is equal to 1. This is when n is equal to 2. This is when n is equal to 3. N is equal to 4. N is equal to 5. N is equal to 6, and so on. So let's have a look then. So when n is equal to 1, we need to derive a function that's going to give us that's going to give us this. Well, actually, this x right here can be written as x over 1 and to the power of 1 like that, just to keep in the pattern. So our infinite sum, well, we know it's going to have an x in it, and that x is, of course, just raised to the power of n, because when n was equal to 1, like that, we had the power of 1. When n was equal to 2, we had the power of 2. When n was equal to 3, we had the power of 3, and so on. So all we're doing is we're raising x to whatever power of n, whatever n we're at, basically. And, well, how are we going to get these numbers on the bottom here? Well, I don't know if you can see as well, those are just the values of n. So when n is equal to 1, we're dividing by 1. When n is equal to 2, we're dividing by 2. And when n is equal to 3, we're dividing by 3. So we're going to be dividing by n. And this is when n starts from 1 and goes all the way up to infinity. Okay, but now we need to deal with this alternating positive and negative situation, because we haven't included that just yet. If we were to expand what we've got right here, it would all be positive. So how are we going to introduce those negative terms as well? Well, we have to think, how can we get an alternating positive and negative 1 coefficient? Well, if we take negative 1 and we raise it to the power of n, and let's say n is an even number, so we square it, we do it to the power of 4, to the power of 6, to the power of 8, this is always going to give us 1. Negative 1 to the power of an even power is going to give us 1 always. And negative 1 to the power of an odd power, so 1, 3, 5, 7, so on, is always going to give us negative 1. So this is good, because we've got all of the integers included in our powers, and they alternate between 1 and negative 1. So that's really good. Let's think then. So our first term is positive. Our first term is positive. So we need this, basically. We need to have negative 1 to the power of an even power. So if we were to include if we were to just times by negative 1 here, and let's say we did it to the power of n, this wouldn't be good, because for our first term, when n is equal to 1, we would have x to the power of 1 over 1 times negative 1 to the power of 1, which would give us negative x over 1 to the power of 1, of course, which isn't what we have. We've got positive. So we don't want negative, so we can't raise this negative 1 to the power of just n. However, we can raise it to the power of n minus 1, because that ensures, in fact, let's just go ahead and do it. So when n is equal to 1, we're going to get x to the power of 1 over 1 times negative 1 to the power of 0. Now, of course, anything to the power of 0, I should have included it here, actually. Anything to the power of 0 is, of course, just 1. So we're going to have x to the power of 1 over 1 times 1, which gives us this term here. Let's check and see if that works for our next term, so when n is equal to 2. So when n is equal to 2, that's not the pen I meant to use, so when n is equal to 2, we get x squared over 2 times negative 1, now to the power of 2 minus 1, so 2 minus 1 is of course just 1, and as we know, negative 1 to the power of 1 gives us negative 1. So this is going to turn into times negative 1, which will give us negative x squared over 2, which is brilliant because that's what we've got right here. So we know it's working. Cool. So we've got an alternating positive and negative coefficient here with this this sort of term right there in the sum. So let's neaten things up a bit. And we can write ln of 1 plus x as the infinite sum from n is equal to 1 to infinity of negative 1 to the power of n minus 1 times x to the n over n. Now, you are perfectly entitled to just leave it as this and have this as your final answer. That is perfectly fine, and in fact, that's normally how the Taylor series expansion is written out. So, in fact, you can just finish here. This is perfectly acceptable. I like to go one step further and just neaten it up ever so slightly, and we're going to have ln of 1 plus x is equal to the infinite sum from n is equal to 1 to infinity. Now, this negative 1 to the power of n minus 1, so negative 1 to the power of n minus 1, if you know your laws of indices, this can be written as negative 1 to the power of n over negative 1, and this negative 1 then can come out to the front of the sum. And so we've actually got negative 1 to the power of n times x to the n over n, like this. And again, using another indices law, if you've got two things times together with the same indices, so if you had a times n times, a to the power of n times, I keep doing the wrong pen. If you have a to the power of n times b to the power of n, this will give you ab to the power of n. And that's exactly what we've got here. We've got a and we've got b right here, both to the power of n. And so this is going to just simplify to the negative sum from n is equal to 1 to infinity of negative x to the power of n over n, like this, and we are done. So those are our two answers. You can choose 1 or 2. Doesn't really matter which one you choose.